All right, cool. So number 20. I really, really like this problem because it hits so many bases that you need to understand. All right, so let me do this. So I'm going to pause recording for 1 second. There we go. Okay, cool. So here's what's happening. So if you read through number 20, probably too blurry for you to read, but so we've got a block of mass M that lies on a horizontal frictionless surface. So let's start there. Let's make a drawing of this. So here we go. Here's our block. Horizontal frictionless surface. Here's the mass M. And it is attached to one end of a horizontal spring with a spring constant of K, whose other end is fixed to a wall. So it's telling me that you've got a vertical wall with a spring constant K. The block is initially at rest at the position where the spring is unstretched, x equals 0. When a constant horizontal force F in the positive direction is applied to it. A plot of the resulting kinetic energy of the block versus its position x is shown in the graph at the right. The scale of the vertical axis is set by Ks equals 4, which is stupid AP book for saying this top number up here is 4 joules. Cool. All right, and then so we want to figure out both the magnitude of F and the magnitude of K. Follow? All right. So one of the things that I guess I would say here is the graph is showing me that as my position increases, right, because I'm pulling it to the right. So, as my position goes this way, the position is going to increase. And the graph is showing me that the kinetic energy increases and then decreases back to 0, right? Okay, and based on that graph, it's asking us to figure out what is the spring constant and how much force are we applying. All right, so when you look at a graph, there are 3 things that you should always be thinking. Okay? Anytime you're looking at a graph, there are basically 3 bits of information or 3 things you can do to the graph. Thing 1 is you can just read the graph, like read the coordinates of the graph. Okay? So, for example, this coordinate here is telling me that when the object is at a position of 1, the kinetic energy is 4 joules. Okay? So that's one of the things you can do. You can find the slope at a point. Right? And sometimes that means something, sometimes it doesn't, right? Depending on the type of graph. And you can find area under it. Again, sometimes that means something, sometimes it doesn't. Cool? So, with that in mind, let's pick some points on the graph that seem significant. So I've already kind of, everything here corresponds to that point there, right? All right, so what are some other points that might be significant here? What other x values do we care about? The maximum, so at x equals 1. Love it. So let's focus on that for a minute and see what we can figure out at this point. Okay, so what do we know at x equals 1? Well, we know that our kinetic energy is 4 joules. So I've read a coordinate from the point. What else is important about that point, you guys? Yeah, we got the slope is 0. Yeah, the slope is 0. Okay. So do we have, is there a thing where we look at the derivative of kinetic energy with respect to position? Like, does the slope have any direct meaning? I don't think it does. Right? Because if you take kinetic energy over units of meters, I don't know that that necessarily has meaning. Okay, what were you saying? Oh, right. If you're at your kinetic, if your kinetic energy is at a maximum, right. So this is a maximum. That's a maximum kinetic energy, and that means that my velocity is at a maximum, right? It has to be, because kinetic energy is 1/2 mv squared. So your maximum kinetic energy occurs at your maximum velocity, right? Okay. Oh, and if our velocity is at a maximum, that buys us something else. So don't shut it out. Everybody think for a minute. Why is the velocity being at a maximum important? What does that mean? Maximum velocity. All right. Thoughts? I'm not trying to ignore it. I just want to get other people too. think back to, like, what would it have been, chapter 1 or 2 of this class? Like way back at the beginning, either your velocity is max, your acceleration is 0, right? Does that make sense? Right? Because maximum velocity occurs when you stop accelerating, right? Okay? Oh, right on. So that means my acceleration is 0, which also means, based on Newton's first law, that the net force is 0. Good? Oh, so we should probably think about how this drawing here is going to look different at this point here, right? So let's do that. So, I wonder if it'll let me do this. Oh, that's wasting time. I'll just draw it. All right, so here's my new drawing. All right, so what forces are acting on my block at this point, at x equals 1? Constant force F and the force of the spring, right? Everybody good up to there? All right, cool. And we know that our net force is 0. Perhaps I can use that to come up with an equation that will use my 2 unknown variables, right? Oh, incidentally, I just sort of stumbled on a thing. There are 2 unknown variables. How many equations am I going to need? 2, right? Okay. All right, so let's see. So if our net force is 0, net force equals F plus force of the spring, right? So let's see, our net force is 0, F is F plus the force of the spring. How do I find this force of the spring, you guys? Yeah, force of the spring is negative kx, right? Oh, and x is 1. We've got 0 equals F minus k. Holy camoli, F and k are the same number. Different units, but same number, right? That feels like useful information. Good. All right, awesome. So we have successfully thought about one point on our graph, and we used that to come up with an equation. We now know that F and K are equal, right? Any problems up to there? All right. So now I feel like we should probably consider another point, don't you guys? Okay. So what's another point that kind of jumps out at you guys as perhaps being useful? X equals 2. All right, so at x equals 2, we know that our kinetic energy is 0. So I've read my points. I don't know the slope there, do I? It's a curve, so there's not a way to find it, is there? Okay. So that doesn't help us at all. Any other thoughts? Sorry, I'm not trying to ignore you. I just wanted to get. Yeah, what do you got?
The change in kinetic energy is 0, so your network is 0.
Yes, that's exactly right. Look, our kinetic energy started at 0 and ended at 0. That means our change in kinetic energy is 0, which means that our net work is 0, which means the work done by the applied force plus the work done by the spring has to add up to 0 because those are the only 2 forces doing work. Follow? All right. Everybody good with that? So now we got to come up with a way. How do we figure these out? Let's see. So let's figure this down. So the work done by the force. Let's talk about what the drawing looks like. I guess I should have made that. We'll go down here and do it. X equals 0. X equals 1. X equals 2. What forces are there? Pull. And the force of the spring. So I kind of glossed over a fact that I wish I had maybe spent a second on when I did this a minute ago. Does it make sense to you why this sort of represents the point where it's moving the fastest? Like, what's happening for the first 1 meter? Somebody explain to me why the kinetic energy is increasing for that first 1 meter. The force of the spring starts at 0, right? Because you haven't stretched it yet, right? And then the more you stretch it, the bigger the force of the spring gets, right? And so for that first 1 meter, the applied force is winning, so it speeds up, right? Does that make sense? And then after that, then the force of the spring is winning and slows it down until it stops again, right? Make sense? Okay, so awesome. All right. So somebody tell me, how would I calculate the work done by the applied force as it goes from 0 to 2? Ouch, that hurt. The work done by the applied force. What's our expression for that? Yes, force times distance, right? Look, we're pulling it that way with a force F. The distance is that way 2 meters, so it's just force times distance, right? Oh, so it's just going to be force times 2 meters or 2F, right? Cool. Now, unfortunately, finding the work done by the spring is not quite as easy. Why? Why is it harder to find the work done by the spring? Because the force changes. It's not a constant force, right? So, to calculate the work done by the spring, we can't just do force times distance. So, if the force is not constant, remember, you can either take the area under the force versus position graph, force versus position graph, which we don't have, or what? What did you say? Sorry? Oh, gotcha. Yeah, we can't unless you have to break it up into infinitely small changes in position, which is the same as taking an integral. Does that make sense? So this is the integral of the force of the spring with respect to position, right? All right. Really quickly, a side note, when I went over this yesterday, somebody had already watched video 9.2. And they said, well, isn't the work done by the spring the same as the opposite of the change in elastic potential energy? And it is, totally is. But at the time of this worksheet, you hadn't learned that yet. So let's figure it out. So here we go. Integral of what's the force of the spring, you guys? Negative kx, right? Right? Oh, and I want to go from 0 to 2 meters, right? Oh? So what's the integral of negative kx? So when you take an integral, your exponent should get bigger, right? Derivative, it goes down. Integral, it goes up. So it's going to go, my power right now is 1, so it's going to go up to 2. But then I got to make sure that my coefficient works out. So I think you end up getting negative 1/2 times kx squared, right? Because then if I take the derivative, I'm going to get negative kx, which is what we want, right? Ooh, and why am I excited? What is this? That's the elastic potential energy equation, right? But the opposite of it, right? Okay, so I need to evaluate it at 0, and I need to evaluate it at 2. And so I'm going to get negative 1/2 times k times 2 squared, which is negative 2k. Follow? All right, cool. So now I got to combine the two. I know that the work done by the force and the work done by the spring have to add up to 0. Here's the work done by the force. Here's the work done by the spring. So, reiterating, the work done by the force plus the work done by the spring have to be 0. That means 2F minus 2K is 0. That means 2F equals 2K. First word. Why am I unhappy right now? We got the same stupid equation we got a minute ago. That worked for nothing. Damn it. Fudge. Ah! Yellow unhappy. All right, so that didn't work. We double found the same thing that we already knew. Thoughts? Sure.
We can go back to the original graph, and we know that.
There's only one graph.
Yeah.
The original. Okay. Oh yeah.
Yes,
Right.
I know.
Sorry.
We know that-
Yes. Go ahead. I'll shut up.
On that graph, we know that the change in energy is also the change in work, and the change in work is the force.
Change in work is the force. I don't think that's true. The work is the integral of the force. But the work and the force
The
are not.
derivative, but the slope of the work is the force. I got the right answer. I did.
I believe you.
I got it.
I believe you, but I also want you to be able to verbalize it. So I think you're in the right neighborhood. Alex, what do you got?
Could we find, like, because it starts off with elastic potential energy or zero kinetic energy, could we find the elastic potential energy and then assume that one because the kinetic energy is the max, that all of that potential energy is kinetic energy?
Say that one more time. I initially was
So
thinking
at
one.
zero, there is no kinetic energy, so it's all potential. And then at one, the kinetic energy is the maximum that it would be on that graph, so then all that potential must be kinetic.
I gotcha. So I hear what you're saying. There's one issue though. How much is the spring stretched initially?
Zero.
So how much elastic potential energy is there? None, right? So this is not a conservation of energy problem, right? It's not, oh, my elastic potential energy gets converted to kinetic energy. Okay, it's not conservation. Why not? Why is the total energy changing?
Could we use that to find the spring constant?
Let me come back to that in 1 second. Why isn't the total energy here constant? You guys, this is really important. There's a non-conservative force. That applied force is changing our total energy. Okay, so when you said use that to find the spring constant, what do you mean, use what?
Well, could we use the elastic potential energy equation so that we can
So, no, because we don't necessarily know, there's no point at which we know so the maximum kinetic energy that we achieve is 4 joules. We don't necessarily know that our maximum elastic potential energy is 4 joules at any point. Do you know what I mean? Because this isn't just about converting KE to EP or vice versa. Because you've got this other force. So I'm sure there probably is a point in here where the elastic potential energy is 4 joules. I legit don't know where it is. Like, I really don't know where it is. Because I don't think there's enough information. Do you see what I'm saying, Alex? Yeah. Okay. Yeah, what do you got? So, in general, all forces are non-conservative except for gravity and the force of the spring. Because those are the 2 types of forces that have a potential energy associated with them. Do you know what I mean?
Yeah.
Gotcha. Okay. So yeah. So really, unless the problem explicitly says this is a conservative force, the only other forces that are conservative are gravity and spring. Okay? Right. So, Alex, are you good with what I was trying to say there? Okay. Charlie, did you?
I've been trying to do it in my head.
Okay. Okay. A little tangled up. Okay. Rachel, you had your hand up before. Did you have a thought? No? Okay. All right. So, oh, Kate? There you go. Yeah. So this process that we did over here at x equals 2 didn't work because it gave us something we already knew. But we haven't used that process up here at x equals 1 yet. Right? So let's try that. So I'm going to go back to the red again. And red. Oh, it'll fell. Oh my gosh. There we go. Okay, so back at x equals 1. We know that our kinetic energy is 4 joules. And so then what I can do is I can say, all right, well, my net work is my change in kinetic energy, which, oh, well, it's going from 0 up to 4. So my net work has to be 4 joules, right? Follow? So that means the work done by my applied force plus the work done by the spring has to be 4 joules. Okay, so now let's do the same thing we just did. How would I write an expression for the work done by the applied force as I go from here to here? Force times distance, and what's my distance? 1. So, oh, this is F times 1. Oh, that's F. All right, cool. Now we got to find the work done by the spring. What did we have to do last time to find the work done by the spring? We had to integrate. Why couldn't we just multiply? It's not a constant force. All right, so this is the integral. Ooh, this is the integral of the force of the spring with respect to position. That's the integral of negative kx with respect to position. That's negative 1/2 kx squared, evaluated at 0 and at 1. Did I do that too quick? It's the same calculation we did a minute ago in blue. Let's see, and x is 1. Well, at 0 you get 0, and at 1 you get 1. So, oh, so the work done by the spring looks like it's negative 1/2 k. Right? All right, so I'm nervous. Yeah. All right, yeah, that'll work. Okay. F and K are equal. Oh, it's because it's not 0. That's what I was missing. Okay, cool. All right, sorry. All right, so the work done by the force plus the work done by the spring had to be 4 joules. I was thinking it was 0. That was what messed me up. Okay, so the work done by the force we decided was just F. The work done by the spring is negative 1/2 k. That has to add up to 0. So there's my second equation with 2 variables. Damn it, I did it again. Thank you. Thank you. Follow you guys? All right. So now, as Rachel said, oh, and I know F and K are the same, right? So either change F to K or K to F. Doesn't matter. So now I've got F minus 1/2 F equals 4. That means 1/2 F is 4. F must be 8, which means K is 8. Follow? Yeah,
It doesn't take too long to explain. How do you know at the beginning that K has to be
we figured that out. Oh, let me see if I can find it. So when we looked at this red point originally, whoa, that's not what I wanted to happen. So when we looked at the vertex of that graph, we discovered that our velocity was at a maximum, which meant the acceleration was 0, which meant the net force was 0. You good up there? Yeah. So then if you write an equation and say net force equals the applied force plus the spring, our net force is 0, the applied force is F, the force of the spring is negative K times 1, and it solves out to give you F equal K. Follow? So that was a weird thing about that. In general, this is not true. It happened to be true for this graph. Usually it's like F equals 3K or F equals 8K or whatever, you know. And you just substitute it in. It's all the same. Good? All right, did this make sense, you guys? All right. I like that problem, A, because it hits a lot of bases. Like there's a lot of like AP physics tricks in here. I like that. I like the fact that you can get the same equation, that F equals K, we figured that out 2 different ways, right? Once by looking at the slope at the vertex, and once by looking at the total change in kinetic energy for the full 2 meters. And the first time I solved it, I did that, and I was so mad. And it took me a minute to realize that you could go back and look at the other one. So, learning those tricks of things that you can do with graphs is super, super important. thinking about what is the vertex and what does that tell me? What does the change tell me? What does the slope tell me? What does the area tell me? All that kind of stuff. When you're looking at graphs, those are the things that you need to be thinking about. Questions, you guys? Sorry? Oh, yeah. So what'd you do? Oh, let me stop recording over here. Go ahead. Oh, sure. Yeah. I don't know. Yeah, come on up. Let's do it. You know what? Keep recording. Boom. Boom.
This is how I did it, because there's the original graph, like that,
Right.
and I figured, well, that if you look at the height at any point, that is the, also the total, the net work that has been done.
Right. So starting at 0 and going up to whatever. Good.
The height at any point is the net work up until that point, and we know the net work is the sum of the f with respect to x. You can, so.
What does that F there represent?
The net force.
Okay, good. Net force. Do me a favor and put a squiggle in front of it. F, so I know it's net force, not the applied force.
So, yeah, the net force, which looks like that, which is what we expected, net force 0 at that point, the clearly negative force here, but we know that the integral of that thing gives us work, right?
Gotcha.
But because we took the derivative to get this and then the integral to get this, these are the same graph.
Right.
Work with respect to x.
Okay.
So, and the slope of work is the force. So we know that this point and that
Right.
are all the same. I found the equation of this parabola.
Oh, gotcha.
Took the slope
Oh,
at
okay.
that point to get the force, and the initial
Awesome.
force
Love it. Yes.
was only due to the applied.
Yeah. So really quickly, you guys, I don't know if you guys were listening with what Charlie just did there. Another thing you can do is, if you assume that that shape is a parabola, then you can use pre-calc skills to find the equation for the parabola, and then have an equation for the kinetic energy as a function of position and go that way. Totally. Did I cut you off?
I was wondering if we could assume that's a parabola.
I don't know that you can. It doesn't explicitly state that. I mean, yes, it does happen to be a parabola.
I think it would be though, because we know that the
Well, I agree. It is. I don't think it's trivial why.
net force is the force we apply, which is a constant force that never changes.
Gotcha. Yeah.
Plus,
So I think,
X,
yeah. So I think if you wrote it as
it's going to have a
linear.
If this,
Yes.
if this maybe did shift and instead did that,
Right.
this would not be a parabola. That would be a conic.
Right.
Not a conic, would be a cubic.
Right.
Then we wouldn't know.
Gotcha.
But
Yeah. So did you see what he just said there? Correct. Yeah. You have to do that. All right, you guys. I talked longer than I meant to. I'm sorry. I hope this was good. Is this helpful? Yeah. Okay. I don't know why you just were looking at me.
I wasn't paying attention to these meetings. I just feel like that's gonna throw me off.
Okay. Oh, that's fine. Okay, cool. All right, guys, so, the next thing you've got to do is worksheet 9.2 due tomorrow. If I remember right, that was a little bit shorter, isn't it? Cool. Good. All right, the nice, like, accommodating side of me wants to go, are we good with the schedule? Unfortunately, I don't know that that's like, if you were to say no, I think my response at this point has to be, sorry, it's where we're at. So, I'm sorry, this is where we're at, yes. But, thank you for understanding.
It's like that for every other. Like, more often than I can do a better job of, making my so
Thank you. All right, you guys have a good one, and I will see you tomorrow at whatever time I will see you.
Aren't we all? Sometimes you go to bed last night.
How you doing, Alex? Good weekend? You're not, in prison. How are you? Oh, sorry about that. Did we get anything exciting? Oh, okay. You for town or? Cool. How are they? I guess.
Okay.
I gotcha. See you later. Thanks, Alex. Good work today. Yeah, you're welcome. I will see you tomorrow, yeah? Cool. Have a good one. How are you, sir? Excellent. I will get out of the way. How are you doing? Nice to see you. Don't do it that. Morning? Still morning? You guys say morning? It is morning. Hey, how are you? I would like to high five or hug you, but I can't because of COVID. But how are you? Chilling. What? Sweet. Okay, well, virtual high five then. Congratulations. Yeah. Really cool. So is that for you? And it's done. Yeah. That's cool. Giant sigh of relief. Congratulations. I'll talk to you later. I like those pants too, not in a creepy way, but. Hello, how are you? Hey, how are you? Super, super. Right. Hello. Whoa, across the street. Hello. Very good, thank you. Okay, how are you? Okay. Hello. Great. Great. Hello? Hello? What about yourself? I do, yeah. I just keep them right here. Not scrabbling and yeah, we're back. Thank you for taking it with us. Sorry. Hello, how are you? Go upstairs and walk. You'll see. Good morning. Is there anything I need to tell you guys that I haven't already told you? Oh, passes. If you need a whole pass until you get started, they're over here. They're actually here now. I think they weren't last time I saw you. There you go. Let me know if I can do anything else yet with physics and or math or maybe chemistry. Otherwise, I'm be doing stuff up here, but please don't hesitate to ask if you need help. Oh, I'm still recording.